For all the cyclic molecules we've dealt with so far, we've just drawn them as rings. For example, for cyclohexane, we've literally just drawn it as a hexagon. So we've drawn cyclohexane like that. Now we know from the last several videos that all of the bonds for a carbon don't sit in the same plane. If we take the example of methane, that's the simplest example. You have your carbon sitting in the middle. You'll have kind of a hydrogen popping out like that, another hydrogen that's in the plane of the screen, another one that's behind the screen, and another one that is straight up. So you kind of have this tetrahedral structure. And in the case of methane, you have that 109.5 degree bond angles. Carbon likes to form bonds of this shape. It won't always be 109.5 degrees. It'll be something close to it, depending on what the different atoms or molecules are that it is bonded to. So given that, what would a cyclohexane molecule actually look like if we try to visualize it in 3 dimensions? So to think about that, let's think about these 2 bonds first. I'll try my best to draw it in one of its 3-dimensional shapes. So those bonds right there, I will draw like that. And then this down here in orange, I will draw like this. And then this up here in magenta, I will draw like that. And then let me see in purple, I'll do these 2 right over here, and I'll draw them like this. So you have that and like that. So hopefully it makes clear that over there is that end over there. This end over here is this end over here. And this way that I've drawn the cyclohexane is called a chair configuration. Chair shape. And it might be obvious. It looks like a chair. That's the back of the chair. This is where you would sit down on the chair. And I guess the back of your calves would go against here. Your knees would sit on it someplace like that. That's called the chair configuration. Now, another configuration that it could be in is called the boat configuration. The boat. And so if I were to put this exact one in the boat configuration, if I take it from a slightly different perspective, if I'm looking at it kind of head on, it would look something like this. In the boat configuration, it would look like this. It would, now I want to use the purple. It would look like that. Now, the first thing you're probably saying is, Sal, you said that the reason why it looks like this is because carbon likes to form these kind of tetrahedral or this tripod-shaped bonds. I don't see the tripod-shaped bonds either here or here. Let me draw that boat a little bit, at least this end of the boat, a little bit better. There you go. And you say, well, I don't see that tripod shape over there. And to see the tripod shape, you just have to draw the hydrogens. So let me draw some hydrogens here. So let me draw a hydrogen here that will go straight down like this. A hydrogen that goes straight down over here. A hydrogen that goes straight up over here. Straight up over here. Straight down over here. Straight up over there. I've now drawn one hydrogen on every carbon. And now let me draw some hydrogens. Let me draw a hydrogen here that goes, straight up, not up, really to the side over here. So a hydrogen there. Let me draw a hydrogen over here that does the same thing. So those guys have their hydrogens. A hydrogen right over here. And then, let's see, this guy needs his hydrogens still. So he'll have a hydrogen that goes down like that, and a hydrogen that goes like that. And then this guy will have a hydrogen that goes like that. And now when you see it like this, if you look at any one carbon on this molecule, if you look at any one carbon, you can see that it's forming the same tetrahedral shape, that it has a tripod at every one. Over here, you have that close to roughly 109, 110 degree angle between each of the constituents that are bonding to the carbon. Now, I've drawn the different hydrogens that are coming off of these carbons in different colors, and I've done it for a purpose. The ones that are going straight up or straight down, we call those axial hydrogens. Axial hydrogens. And the ones I drew in orange that are kind of going to the side in some level, we call these equatorial. These are equatorial hydrogens. And there's a reason why it's useful to know that name is when we talk about the different configurations, the different chair and boats, whether something is equatorial or axial can change if this were to flip up or vice versa and things like that. And we'll talk more about that in the next video. And the reason why they're called equatorial is if you think about it, and it's sometimes hard to visualize, this bond right here is parallel to this bond right over there. And this bond right over here is parallel to this. It's parallel. The equatorial bonds are parallel to some part of the ring. So that one is parallel to that right over there. Actually, I could even color coded that. This, well, I don't want to use that same color. This is parallel to this, and this is parallel to that. And we could do it for all the equatorial bonds. So for example, I'm running out of colors here. So this right here is parallel to this and that over there. So we could keep doing it for all of them. I could do it one for the other set right here. This guy right here is parallel to that guy over there. I didn't quite draw it like that, but hopefully it makes the idea clear. And I'll do one more of these just to show what's parallel to what. This bond is parallel to that. So the ones that are parallel to some part of the ring we're calling equatorial. And the ones that kind of jump out of the ring that aren't parallel to any other part of the ring, we're calling those axial. And the way I've drawn it here, the axials are the ones that point up and point straight up and point straight down. And we can do the same thing on a boat configuration. Now, one question you might ask is, well, there's these two configurations. Both of these would result in tetrahedral type shapes at each of the carbons. In fact, let me draw it for you. So we would have, so this axial hydrogen is pointing straight down. This one is pointing straight down. Here, this hydrogen is actually going to point straight down because we've flipped it up. And then over here, you would have a hydrogen points straight up, and then one that's kind of pointing down. This gives a tripod there. To have the tripod over here, you'll have to have a hydrogen that points a little bit like that, one that points a little bit like that, one that's pointing a little bit like that along. Well, you can kind of view it along the same plane as this guy would be parallel. It's hard to see it in this, but he would actually be parallel to that. This guy would be out like this, and then this guy would have an axial hydrogen, and then he would have one equatorial one just like that. So you could draw the tripod shapes in either the chair or boat configuration. But one question is, well, what's more stable? That's actually one of the main points of being able to visually think about the three-dimensional structure of any of these hydrocarbons, or in this case, cyclohexane. So in this situation, we know from past videos that all of these carbons with their hydrogens around them, these bonds, these have electron clouds around them. The electron clouds are negative, and so they want to get as far away from each other. They want to get as far away from each other as possible. In this chair configuration, you have this carbon up here. This carbon, the CH2, we could consider it has two hydrogens and it's connected to the rest of the ring. It's as far as possible from this CH2 as possible. So in that situation, we have a lower potential energy, or it is a more stable shape, or more stable configuration. In the boat configuration, this CH2 up here is much closer to this CH2. I mean, that's really the main difference between the two. And they want to get away from each other. They want to repel each other. So this one will have higher potential energy, or it will be less stable. Less stable. Less stable. So this is just a starting point of how to visualize cyclic hydrocarbons. And we'll use this information in the next video to think a little bit more about maybe the different chair configurations that a molecule could have and what could be more stable. In this situation, in the case of just cyclohexane, the two chair configurations are equally stable. And let me just touch on that a second. So you have, well, I don't have to, actually, let me see. I won't copy and paste it. I'll just redraw the other chair configuration for this guy. Actually, let me just do it separately over here because I've made the colors here so confusing. Let me draw the same cyclohexane, but in two different chair configurations that it could be equilibrium in. So you could have this one. You could have this one. So this could be one chair configuration. And I'll draw it like this. And then the same hydrocarbon could be or the same cyclohexane could be in equilibrium with this other chair configuration that looks like this. That looks like this. Let me have a little more space here. So it looks like this. And then we do the pink. Goes up like that, like that. Let me make sure no, I want to do it actually. This pink guy goes like this. And then the blue guy is going to be just like this. So notice in this situation, this carbon up here is kind of at the top of the chair, and this carbon is at the bottom. And then they've flipped, but these are equally stable configurations. But one thing to think about is all of the axial guys on this carbon here turned into equatorial on this carbon, and vice versa on the two. Let me show it to you. Let me just draw the hydrogens on this carbon. So if I were to draw this carbon's hydrogens, has an axial hydrogen and has an equatorial hydrogen whose bond would be parallel to that, right? Just like that. And this guy would have an equatorial hydrogen whose bond is parallel to actually both of these guys, and an axial hydrogen. And an axial hydrogen. But when it flips, and I'm just drawing those guys' hydrogens, but when this structure flips like that, what happens? Well, this hydrogen over here goes into this position. And this yellow hydrogen over here goes into this position. So over here it was equatorial, and now it becomes axial. And now it becomes axial. And the same argument can be made over here. This equatorial hydrogen, when it flips, when this whole blue part flips down, now becomes axial. Now becomes axial. And this axial hydrogen, when you flip it down, becomes equatorial. It becomes equatorial. And you can actually do that for all of the hydrogens. Over here you have an axial hydrogen, axial hydrogen. Once you flip it, let's see, you have an axial hydrogen, and then you have an equatorial hydrogen and equatorial hydrogen. When you flip it, these two equatorial hydrogens become axial. So they become axial, and then both of these guys become equatorial. So let me do that in yellow. Both of this guy and this guy become equatorial. So this and that become equatorial. They become parallel to the other end. And you could do it for these two hydrogens as well. So that's another interesting to think about. And this is really just practice on visualizing what's going on when we visualize